All right, yeah, so this is a joint work with Sasha and Karthik. All right, let's get into it. So we're going to be doing an online supervised learning setting where at each time we'll receive a context, we'll produce some real value prediction, we'll receive some abstract label, and then we'll suffer some loss. And the only thing important about the loss is that it's convex and Lipschitz with respect to our prediction. So think like regression or online binary classification with like a convex surrogate. And we're going to fix some hypothesis class, and we're going to be looking at regret against this hypothesis class. And what we're going to be interested in this work is whether our regret can be bounded by the empirical Rademacher complexity of a class we're considering, where the empirical Rademacher complexity is this kind of classical statistical quantity that you all may be familiar with. It's just this thing where I'm going to sample a sequence of coin flips or Rademacher random variables, and I will take the element of my class that's most correlated with these coin flips on this sequence. And so this is well known from the statistical learning setting because for many losses, this captures the optimal sort of instance-dependent rate that you can get. So what we're interested in now is, can we ever hope to get this as a bound on a regret in the online setting on a sequence-by-sequence basis? So for every sequence, our regret against that sequence is bounded by the Rademacher complexity on that sequence. And, when this is possible, can we develop efficient strategies to actually achieve it? So what we're going to show is that to answer the first question, no, this is not always possible because learnability in the online and statistical setting are not the same. But we give a tight characterization of when it is possible based on connection to decoupling inequalities for martingales that will be indexed by the class F we're considering. And furthermore, in the linear setting, we give a new algorithmic framework for developing algorithms to achieve this regret bound. And this is actually sort of fundamentally exploits this decoupling characterization of the achievability of this bound. So this uses a sort of geometric property that Sasha alluded to that would really not be obvious a priori if you didn't have this martingale perspective on the whole problem. So let's focus on an important special case, which is linear classes. So in this case, our data is just going to belong to some Banach space with some norm. This is just some vector space. And our hypothesis class is just going to be the set of all linear predictors bounded in the dual norm. And in this case, we have this convenient expression for the Rademacher complexity, which is just the expected norm of this Rademacher average. So how might we develop algorithms that achieve this bound? Well, the perspective we can take in light of sort of Sasha's talk is we can think about how do we approach this in terms of, say, like a connection between martingale inequalities and regret inequalities and geometry. So for the sorts of like martingale inequalities and regret inequalities that Sasha was interested in, the right geometric property to consider was strong convexity or like smoothness. But it turns out that to get the Rademacher complexity, strong convexity is not enough, and in particular mirror descent as an algorithm is not enough in general. So we need to move beyond strong convexity and beyond mirror descent. So this brings us to our geometric characterization for this problem. So we have this algorithm called zigzag, and I'll kind of describe the geometry of the problem and zigzag in parallel. So what we're going to look for is a particular function which takes two values in the data space. So we're calling this U. And U satisfies two properties. The first is that it's an upper bound on the difference between the two norms of the points I evaluate the point with, or I evaluate the function with. And the second property is what we call zigzag concavity, which is where the name of the algorithm comes from. And this basically says that if you restrict to diagonals, this function needs to be concave. And so sort of one of the main theorems is that if we have such a U function, you can drop this into our algorithm, and you can achieve the Rademacher complexity regret bound for the class you are considering. And the constant you get here is the same one for which the U satisfies the first property. And the running time for this algorithm is essentially just the running time of computing U, either U or its gradients. So let me simultaneously both prove that having such a U is sufficient and actually describe the algorithm. I'll motivate the algorithm using its proof. So let's just start with regret, and we're going to subtract off the regret bound that we're interested in. And what our goal will be is that we'll try to prove that this whole thing is less than or equal to 0 for the right choice of strategy. So as a first step, we can linearize and collapse like terms, expand some norms out, and what we'll get is something that looks like our linearized loss with a norm term coming from the benchmark and a norm term coming from the Rademacher complexity. So this is a difference between two norms. It's not super easy to analyze. It's not convex nor concave in like the x's, for instance. But the first property of the u function says that we can move to an upper bound on the difference between two norms. So we'll sort of use the u as a surrogate. And the second property of u, the zigzag concavity, says that if we play a particular strategy based on the gradient of u at a point, then we can sort of peel off the data at time n, if we played this at time n, that is, and we'll get something that just depends on the data at time n minus 1. And we can repeat this process recursively throughout time until we get that our regret under this strategy is bounded by 0. So that's cool, but this is still all sort of mysterious. So like, where did this u function come from? Is there like a deeper story to what's going on here? And the answer is yes. So to do this, we need to go back to 1984, where these u functions were first studied, and that's in the context of like probability in Banach spaces. So Donald Burkholder first discovered these u functions in the context of proving decoupling inequalities for martingales. And the particular decoupling inequality we were interested in is what's called a UMD inequality. So this is just an inequality that says that if I look at a martingale difference sequence, taking values in this vector space, if I take a given martingale difference sequence, I can apply like an arbitrary sequence of like sign flips to each element, like before the martingale is drawn, and this can only blow up the expected norm of the martingale by some constant. And so what Donald Burkholder proved is, whatever the constant that appears here, there has to exist a u function, for the same constant. So to recap the sort of characterization we have now, we start off with the UMD property, and via Burkholder we have that UMD holds if and only exists if there exists a u function. But we just showed that existence of a u function implies achievability of this Rademacher regret bound. We further show in this work actually that this Rademacher regret bound, achievability of this is actually equivalent to a related decoupling inequality called a one-sided UMD inequality. But unfortunately, this is actually strictly weaker than the UMD property. So there's technically there's like a small gap between these properties. But luckily for all of the classes we're interested in, these all satisfy UMD with good constants. So we can sort of apply these to develop efficient algorithms to get the rad hat bound. So to give a concrete example, if we're interested in LP norms, we can use this special potential developed by Burkholder in the context of our algorithm. And what this will give you is that you're, if you have some like dual pair of like LP norms, so you have LQ and LP, then my regret against LQ is bounded by Rademacher of LP if I just take the gradient of this. And this takes like O of d time. So most of the strategies we have will take, say, order of dimension of vector space time. They're comparable to like mirror descent. So to look at some applications where this regret bound is good, one thing you can observe is that in the L2 case, the regret bound I put on the previous slide recovers Adagrad. And in the L infinity case, you get sort of like the diagonal Adagrad back. Another nice example is that if you do the L1 L infinity case, so this is like experts, you can get like a lot of different kind of like structural upper bounds on the Rademacher complexity. So you can get things like rank and like max norm of the data. But there's a more general phenomenon here. And this is what we call like sequence optimality of the Rademacher complexity. So if you have a loss like hinge or absolute that's not too smooth, then you can actually show that if I have any strategy whose regret is bounded by some function b of the data, then the Rademacher complexity has to be smaller than b point-wise. So actually, like any amount by which you improve on the Rademacher complexity has to live between 1 and whatever constant the algorithm actually achieves this with. Okay, so just to recap, we have this characterization of like decoupling, u functions, and Rademacher complexity. This is a more general instance of sort of this principle of going between martingale inequalities, pathwise regret statements, and geometric properties. And in particular, if you have an efficient U, you get an efficient algorithm. So here's some closing questions. I won't spend too much time on these, but I just want to encourage you all to think about more instances where you can reduce like a potentially complicated online learning, like algorithm design problem, to a like crisp and simple geometric problem. And from a technical perspective, it's fun to try and think of U functions. So I encourage you to do it. All right, thank you.
Questions? Sebastian?
Is there a principled way to think about the U function that you showed for the epigoal? Like, is it the Bregman of something? Is it, like, where does it come from?
Okay, so like you mean the LP one I had on the previous slide? I don't really know the general principle for this one. Yeah, this would be interesting to think about. It would be interesting to think about, like, yeah, sort of what results of this form maybe could you try to extract using. I don't know about Bregman necessarily. I'd be pretty surprised if that were sufficient. But I mean, this one I can tell you actually. This is actually pretty interesting. So this actually achieves the best possible constant. And the way Burkholder derived this one was by just setting up some like PDE and solving it. So there's actually like a whole community of people in probability that are interested in coming up with these inequalities, because you can use that, or interested in coming up with these U functions, because they actually give an efficient analytic way to like certify best constants for different inequalities. But in terms of like general principles for coming up with them based on things like Bregman divergences, yeah. No, I couldn't write it down off the top of my head. Yeah.
Right, let's thank all the speakers again.